Welcome back to another exciting episode of Dave Does Math from Home. This is part 3 of our video series on section 4.3, where we talk about derivative tests. In our first video, we talked about the first derivative test. In the second video, appropriately, we talked about the second derivative test. This is the video where I want to show you what they look like side by side. And before I get into that, I want to give you a quick disclaimer that I'm not going to ever ask you to do both of these things. The first derivative test and the second derivative test are two different ways to get the exact same information. Both of these tests tell us which critical points are maximums and which ones are minimums. So you don't have to use both of them when you're doing your homework. You can just use one of them and that's fine. I want to do them both for this problem so you can see what they look like side by side. This is purely for your entertainment. So let's get started. I want critical points of this thing. So first thing I need to do is take a first derivative, set it equal to 0. This will be x cubed plus 4x squared minus 4x minus 16 equals 0. And then I'm factoring this. We have 4 terms, it's polynomial. So I can pull out an x squared from the first 2 pieces and a negative 4 from the second 2 pieces. And then I can pull out the x plus 4s. And then I can pull the difference of squares out of this. So I have an x plus 4, an x minus 2, and an x plus 2 all equals 0. Which means that my critical points are x equals negative 4, negative 2, and positive 2. So, we'll start with the first derivative test, because that seems like a good place to start. First derivative test involves a number line. On the first derivative test, number line, I need to put my x values, negative 4, negative 2, and 2. These are what x equals. Above this, I'm going to mark the first derivatives. First derivative is 0 here, 0 here, and 0 here. First derivative has to be 0 at these points. That's what makes them critical points. They're on the number line because the derivative there is 0. So in the first derivative test, I'm going to look at what the derivative is in between these points. So I'll take something like negative 10 and plug that. I'm going to plug it into the factored version because the factored version hasn't fundamentally changed. Sometimes when you go through this factorization process, you edit the equation a bit, like you divide both sides by a negative number or you multiply both sides by something. If you have changed the equation in that way, then you should use the original when you do the first derivative test. If the only thing you have done is simplify it without actually doing anything to both sides of the equation, then you're safe to use the simplified version, which in this case I think is much easier. If you plug in negative 10 for all these x values, you don't care what these values are, you just care whether or not they're positive or negative. So when you plug in negative 10, you have a negative number, and a negative number. And those 3 negatives multiplied together will give you a negative number, which means that the function is decreasing on this interval. When you plug in something like negative 3, you can see that you'll get a positive number here, and negative numbers here and here. And when you multiply that together, you'll get a positive, so the function is increasing on this interval. In between negative 2 and 2, you can plug in 0 to get positive, negative, positive, which will multiply to give you a negative number and a decreasing function. And when you plug in a positive number like 10, you can see that all 3 of these will be positive, and you'll get a positive number, and your function will be increasing. So here at negative 4, it transitions from decreasing to increasing, which means you have a minimum. At negative 2, it transitions from increasing to decreasing, so you have a maximum here, local max. And here it transitions from decreasing to increasing, so you have a local min. And that is the first derivative test. If we were doing this on a test or a quiz, or even on the homework, the question would be asking you what the local mins and maxes are. So that's a question of evaluating the function at these points. So you would need to plug -4 into this original function to get a y value, and you would report that y value as a local minimum at -4. I'm not going to do that for this problem because that's going to be like 10 minutes of arithmetic. That's not a good use of our time in these videos. So if you're curious what these minimums and maximums are, plug these x values into the function to get y values, use a calculator. I trust you to do this. I'm not going to do it right now. I am going to do the second derivative test to make sure that the information we get from that matches the information we got right here. So to do the second derivative test, I need a second derivative. F double prime of x equals, I need a derivative, this is my first derivative, so I need a derivative of this. 3x squared plus 8x minus 4. This is my second derivative. And to do the second derivative test, I just need to evaluate it at these points. So I'll plug in -4, and we will get 1648. Minus 32 is 16, minus 4 is 12. So this is concave up, since this number is positive, which means I have a smiley face, which means I have a minimum, which matches first derivative test. At f double prime of -2, I should get 12. Minus 16 is -4, minus another 4 is -8. This is concave down, which means I have a frowny face, which means I have a maximum there, which again matches our information from before. And f double prime of 2 will give me positive 12 plus 16 is 28, minus 4 is 24, which is concave up, which means I have a min, which matches. So all this information matches. And this is it. This is the first derivative test and the second derivative test all together. I want to re-emphasize that on tests and quizzes, I'm only going to ask you for one of these, and I'm not going to ask for either one in specific. I'm going to leave it entirely up to you to choose one of these things that you think is best and do that one. I do need to see one of them. So if you try a different technique, like if you try to do the section 4.1 stuff, where you just plug numbers in and you pick the big number and say it's a maximum, and you pick the small number and say it's a minimum, that's going to lose you points. I do need to see one of these tests at work, but I don't care which one. The other thing I want to say is you can choose which of these tests you're using on the tests and quizzes when you are asked to find local minimum and local maximums on a problem. The homework is going to make you sort of exercise with both of these by asking slightly different questions. So the homework isn't going to start off by asking you find all the local extrema and identify them as max and mins. The homework is going to start off by asking you to find intervals of increasing and decreasingness. And that's essentially asking you for what this first derivative test is offering. This is an interval where the function is decreasing. This is an interval where the function is increasing, decreasing, increasing. So they're going to ask you for this information without specifically asking you to do a first derivative test to identify maxima and minima. It's also going to ask you a bunch of questions about concavity. It's going to ask you for intervals where it's concave up or intervals where it's concave down. You can find those with the second derivative using this kind of information. Without actually using the test to identify max and mins, you can use this to identify concavity. So the homework is going to make you practice with both by asking questions that are like parts of this. On tests and quizzes, I'm going to ask you to find local extrema using one of the two derivative tests. And then it's up to you which one you want to use. That is the end of my rant about this, but I do want to give you another example since we're only 10 minutes into this video. Second example should be f of x equals 1/5 x to the 5th minus 3x cubed plus 2. So, once again, the larger question I am asking is identify maxima and minima. So we need to start that with a first derivative set equal to 0 to find the critical points. First derivative is going to be x to the 4th minus 9x squared. This is what we're setting equal to 0. We're going to factor out an x squared and an x squared minus 9. So my critical points now are x equals 0, 3, and negative 3. These are my critical points. So I'm going to do the first derivative test, see what that tells us, then do the second derivative test and see what that tells us. First derivative test looks like a number line. We'll put 0 in the middle, negative 3 back here, positive 3 over here. These are x values. Above this I'll put f prime of x, because I know that that's going to be 0 and 0 and 0 at these critical points. That's where the critical points came from. So now I need to look at numbers to the left and right and in the middle of these guys. So let's look at negative 10 again, seems fine. When we plug in negative 10, this is going to be like 100, 91, so very, very positive. It is increasing on the back end. If I plug in something like negative 1, I will get a positive and a negative here. So it's decreasing here. When I plug in something like positive 1 or positive 2, I will get a positive number here and a negative number here again. So it is decreasing on both sides of 0. And when I plug in a number like 4 or 10, I should get a positive number and a positive number, giving me an increasing thing. So let's look at what this means. At negative 3, it switches from increasing to decreasing. That means that here we have a max. At positive 3, it switches from decreasing to increasing, and that means that we have a min. At 0, it goes from decreasing to flat to decreasing, which means this is neither. It's not a maximum or a minimum. The graph is doing this, where it goes flat for just a second, and then it keeps decreasing, which is fine. We've seen graphs that do this. Most cubic graphs do this at some, or I guess I shouldn't say most cubic graphs. The graph of y equals x cubed does this. If you take its derivative, it has a critical point at 0 because it gets flat here for a second. But it's only flat for an instant, and it's increasing to the left of it, and it's increasing to the right of it. That's the same sort of shape we have going on here. I wanted to do this example so that I could illustrate to you the importance of not finding one of these and then just alternating. Because in the other examples we've done, once we found one of these things, the others alternated. So like if this was plus, the rest would go minus, plus, minus, plus. It's a very nice pattern. This one doesn't do that. So I just want to discourage you from trying to use that pattern to skip steps, because you might be wrong about skipping those steps. You got to be careful. This 0 here is like a double root of the derivative, which gives you this sort of behavior. Or what was our word for this in pre-calc? Multiplicity 2. As a root of the derivative, this this 0, this intercept, it's not actually an intercept, this intercept has multiplicity 2, which gives you different behavior than what you might expect. So, knowing now that we should expect some weird nonsense, let's see what the second derivative test has to tell us. The second derivative of f is 4x cubed minus 18x. So I'm going to plug -3 in here, and we'll get -27 times 4 is -100-ish, plus 80-ish is still negative. So I have something that's concave down, which means it's a frowny face, which means this is a max. Which, yes, okay, this matches. F of -3 is a max in both tests. That checks out. F double prime of +3 is, let's see. Oh, I'm over here. +3 cubed is 27 times 4 is going to be a little over 100. Minus 80-ish is still very positive, so this is concave up, which means that we have a minimum which again matches our first derivative test. Let's see what's going on in the weird case, f double prime of 0. F double prime of 0 is 0. That means we have an inflection point, so that's probably useful for something, but it doesn't give us any information about whether this is a max or a min, which is important. The first derivative test gives us information here. With the first derivative test, we can conclusively say that this is neither a maximum or a minimum because it's decreasing on one side and decreasing on the other. Here, this gives us no info, which is different than telling us that it's definitively neither. Sometimes you get inflection points because the graph does this, which is what's happening here. Sometimes you get inflection points because the graph is doing this. X to the 4th does this, where the second derivative of x to the 4th, y equals x to the 4th, the second derivative is 0, and that means that you have a minimum. But the second derivative test doesn't tell you that. So, first derivative test might seem like a little bit more work to some of you, but it gives you more information in these weird niche cases. Second derivative test might seem like less work, but if you get a second derivative of 0, that gives you no information. Maybe it's a max, maybe it's a min, maybe it's neither. You don't know. You have to do something else to solve that mystery. That's it for this video. Hope you've enjoyed. Do the homework, and I'll see you next time.